When observing the Golden Gate Bridge spanning over the Pacific Ocean, your eyes may drawn to its elegant suspension cable system. What would happen to the bridge if this cable system was not present? In short, it would be a disaster. Let's brave the treacherous currents of the Pacific Ocean and construct the Golden Gate Bridge with its chief design engineer, Mr. Joseph Strauss. We will also explore the impressive engineering feats the Golden Gate Bridge has achieved. Join us. The Golden Gate Bridge is a suspension bridge. A highly simplified suspension bridge can be constructed the following way. Build two towers at the both ends of the oceans. Suspend a long cable between the towers. This cable can be resembled as a parabola. Now let's attach a roadway surface made of concrete with pillars. This clearly provides support to the end of the road deck. When we connect the suspension cables between the main cable and the road deck, the bridge is also supported along its length, so the road deck won't fail as we saw earlier. This is the basic design behind the suspension bridge. Before exploring more about the Golden Gate Bridge, let's first understand why the engineers choose a suspension design for this site. The distance between the two coastlines of the Golden Gate is a whopping 2.7 kilometers. Let's construct a conventional beam bridge here. You can see that the road deck is supported by various piers. The presence of these piers blocks the movement of ships underneath. As you can imagine, constructing them 300 feet deep in the water would be extremely costly. Thus, the beam design does not make sense here. Now let's construct an arch bridge. This would definitely provide passageways for ships. However, to maintain the arch shape, the bridge would need to be extremely high. Such a structure would be quite complex to construct. That's why Mr. Joseph Strauss opted for a suspension design, a bridge that could overcome all the drawbacks we discussed in a very efficient way. Now let's get into the design details of the suspension bridge. This design has one glaring issue. If you construct the bridge like this, the towers will bend inward as shown. The main cable is under a huge tensile load. This applies force on the tower. When you resolve this force, you can see that there is an imbalanced horizontal force acting inward on the tower, which explains why the towers bend. Can you find a solution for this issue to cancel this horizontal force? We need the same force acting in the opposite direction. The straightforward solution is to extend the main cable and anchor it down to the ground via an anchorage system. However, we can optimize the financial resources needed to construct this bridge with a simple idea. All we need to do is to move the towers closer to one another. Now the length of the unsupported bridge deck is reduced. Due to this, tension in the cable will be reduced. This will obviously lead to a cable with less cross-section area. The width of the main cables are more than half the height of the average human. As a tourist attraction, a piece of this impressive main cable is demonstrated near the Golden Gate Bridge. However, if you construct the bridge with this exact design, it will experience a premature death. Can you guess why this would be the case? Connections are the weakest part in any structural system. The direct connection of the steel suspenders with the concrete deck will lead to the formation of cracks on the deck, since concrete is brittle in nature. Let's see how Mr. Strauss solved this problem. Mr. Strauss decided to connect the suspenders to a steel structure. Steel-to-steel connections is always strong. The details of the connection between the suspenders and steel structure are illustrated here. The road deck is placed on this structure. Mr. Strauss kept the width of the road to 27 meters to account for current and future traffic demands. Assembling the structure like this was far from an easy task due to foggy and windy conditions at the site. To facilitate the process, workers prefabricated each member of the truss and brought them to the site, where ship's assembly of the individual members was accomplished using a derrick, and their connections were secured via rivets. To ensure the safety of the laborers, a net was installed underneath the bridge deck. As the construction of the bridge progressed, they simultaneously connected the structure with the main cable using suspension cables. Moreover, to maintain equal loading on the cable, workers had to assemble the system simultaneously and equally in two directions for each tower. Thus, the Golden Gate was bridged. 250 pairs of vertical cable were used and they hung the whole bridge deck to the main cable. After the construction of the steel structures, the workers painted the bridge a special international orange color. Next, let's examine some details of concrete road construction on top of this solid structure. Workers first laid down wooden form. With that, they attached steel bars, welded them to the steel sections below them, and later poured and compacted the concrete using a needle vibrator. Our bridge looks perfect now, but is it ready to support vehicle movement? Not yet. We must first tackle another major engineering challenge: thermal expansion. The concrete and associated steel structure will expand or contract based on environmental temperature variations. If we had constructed this bridge as a single piece during a hot sunny day, the bridge would expand and cause tremendous stress on the tower as well as on the road. Eventually, the bridge would experience damage. If you have ever visited the Golden Gate Bridge, you may have noticed peculiar connections on the road. These connections, called finger expansion joints, were Mr. Strauss' solution to solve the thermal expansion problem. Mr. Strauss divided the deck into 7 separate pieces. You can see this bridge has 3 cradles. The finger expansion joints are installed between the gaps. During an extreme temperature increase, the length of the road deck increases, and these joints move by almost 4 feet. What an elegant solution for a serious issue! However, there is still a small problem to solve. The thermal expansion of the steel is slightly higher than that of concrete. This differential expansion can cause trouble for the concrete deck, which is composed of a mixture of concrete and steel bars. But this expansion issue is negligible when the length is small. This is why the Golden Gate contains tiny expansion joints every 50 feet. Another great design challenge Mr. Strauss dealt with was the height of the tower. Let's do an experiment to gain a better understanding. I had 2 bridge designs with me. A tall tower design. It is having a high sag, and the next one, a short travel design. Obviously, a small sag. The question is, which design gives more strength to a suspension kind of bridge? Let's test the first design using a road deck. A really heavy road deck. When I attach the road deck, this design is standing strong. This design is safe now. Let's address the same weight to the next design, to the short arc design. This bridge went for a sudden failure. I couldn't react to that, so in short, we produce experimentally. The tall tower design is the best design for a suspension kind of bridge. It's more strong. The question is, why to get answer for this? Let's invite the Chief Engineer's Hall project, Mr. Joseph Strauss, to the video. The major difference between these 2 designs is the angle of the cable in both. The load to be carried is the same. The vertical component of the cable tension balances this weight, since the small tower design has a low angle to balance the weight. The cable has to induce more tension. This is why the short tower fails during the experiment. The tall tower will obviously reduce the tension in the cable, but it will cost much more to construct it. That's precisely why Mr. Strauss calculated the optimal tower height of 746 feet, a happy average between these 2 scenarios. Now let's get into the most exciting part of this video: construction of the Golden Gate Bridge in a hostile environment. First, we start the tower construction. Did you know the construction of the south side tower was tougher than the north tower? This is because the south tower construction had to overcome the violent Pacific Ocean. A tower foundation must be constructed on strong bedrock called hard strata. For the south side, the hard strata was 50 feet below the seabed level and had a steep floor. We need to dig this deep and build RCC foundation for the South Tower. To do so, first, professional divers were hired to blast bombs underwater. The divers cleared the debris of the explosion and made a better surface. Now, it's time to construct a steel and wooden framework on this surface. The divers obviously did an amazing job here. Now let's say the cross-section of the structure they built. Then the concrete was poured to create something called fender walls. Afterwards, all the inside water was pumped out. Now that the fender wall is ready, can the workers go inside and start digging for the hard strata? Here is the issue. The ocean currents are so nasty that the fender wall will have to bear a huge inward force and can collapse. This kind of construction is highly unsafe. Mr. Strauss had a clever idea. Initially, they placed the blasting tubes, the workers' shaft, and the material shaft inside the fender walls. The trick was to construct a thick, reinforced concrete slab so that workers can work beneath it. The way workers reached the workers' chamber was quite interesting. It was via the workers' shaft. They continuously drilled the boulders and dug underneath the RCC slab. This RCC slab supported the fender walls and protected the workers underneath against deadly currents. During this process, the entire fender wall structure was allowed to sink slowly. You can see its knife-like shape. Eventually, they reached rocky hard strata. After leveling the hard strata, they made a steel structure there and built an RCC foundation. The construction of the complete foundation is quite easy now. You can see how the fender walls project the main foundation from the deadly waves. Now it's time to see the construction of the gigantic towers. Once the foundation was ready, they assembled the steel base plate on it. Now comes the magic of these hollow steel cells. They assembled and riveted these cells as if they were constructing a tower using Legos. Now you can see how clearly they had to plan the shapes and sizes of these cells so that the tower would finally achieve the shape which it was intended to achieve. Mr. Strauss designed this unique cellular structure to be economical as well as strong. The tower construction was then complete. Next, it was time to lay down the main cables. For this, they first installed cable saddles atop the towers. You may think that the main cable is a single solid cable. The main cable is in fact made up of 27,000 smaller wires and a total length of 129,000 kilometers. Length of steel wire was consumed for fabrication of it. To start laying these cables, workers first constructed a catwalk bridge for themselves. At first, workers laid a support wire. The main cables made their journey via these snipping wheels. Furthermore, these small wires were passed over the tower through the cable saddle one by one and were then clamped by laborers. Then the workers pressed the wires tightly using a hydraulic press. They simultaneously wound the wires together using galvanized steel wire, which is why the main cable looks like a single large pipe. These cables are anchored to the bedrock with strand shoe steel plates. After laying the main cables, the suspension cables were attached to it. All that was left to do was to construct the deck structure and lay down concrete for the road. You already know how they did that. A strange incident happened on the Golden Gate Bridge on its 50th anniversary when more than 300,000 people gathered on the bridge all at once. You can probably predict what will happen if a suspension bridge is overloaded. Overloading a suspension bridge can cause it to sag. This is why this can even cause the main towers to bend inward. This is exactly what happened on that day. The road deck sagged by almost 2 meters. Even with this extreme load, Mr. Strauss' incredible suspension bridge stood strong. One can only admire the technologies they developed 89 years ago in the design and construction of the Golden Gate Bridge. This successful project signified a leap in civil engineering.